dynamic models now, sort of longer time horizons than 2-period. We're going to look at, this is a really nice paper. It's a single agent paper, so it's going to be, it's going to have dynamics, but it's going to be less about those frictions like commitment and asymmetric information aren't really going to be there. It's going to be more about politics, like what is the regulator maximizing. Then I'll have this paper I wrote with Claire Lim that has a bunch of these things going on. Then we're going to shift into environmental regulation, and these are going to be mostly about, not about asymmetric information or commitment, just about environmental regulation. Okay. What they have in common is they've got investments or some type of forward-looking behavior by the agents. Okay, so the setting is California water. It's like WOLAC. So even though it's the same sector and same state, it's actually quite different because he's looking at water utilities that are owned by the city. Okay, so it's not a private firm being regulated. Here the regulator is essentially the firm. Okay, but the regulator / firm faces incentives that are different than making as much money as possible because they don't get to keep the money for themselves. They have other incentives like getting reelected or avoiding conflict with their constituency and so on. And his starting point is going to be that he's going to see pretty straightforward evidence that we'll look at that water is priced too low, like below cost. And with that, the question is like, what's going on? Why are they doing that? Okay, and what would it be like if they did something potentially more efficient? So here's some underlying data. So each one of these are different municipalities in California that own their water utility and run their water utility, municipal water utility. And he sees them at different, several periods, different amount of periods for each one. Here he's calculating, so he's basically taking their administrative marginal cost data. Okay, so they report variable costs. He basically divides that by quantity and says that's the marginal cost. Okay, and he's subtracting from marginal cost price. Okay, so this should typically be negative, right? Price should be above marginal cost, but these are all positive. Okay, marginal cost is above price. If you do it as a fraction of marginal cost, you'll even see some places where they're basically pricing at 0. Okay, so you don't pay for water. That happens. Below marginal cost. Yeah. That's the whole thing here is that you're pricing too low. Okay, so think of like you're trying to make some portion of your customers really happy by giving them free water. Okay, so here's a very simple graph. Okay, this is for one of the cities, for the city of, this is the city of, I think it's Delano. I don't remember it exactly. I should have put it on there. Yeah. Okay, so here's their reported marginal cost. Here's where they're pricing. Okay, and one of the points the paper makes is the marginal cost they report is not actually the full marginal cost. Okay, because the technology that these firms use, these cities are not totally randomly selected. These are all cities that not just own their municipal water utility, is that they get the water from the ground underneath them. Okay, so it's not coming from some mountain or some reservoir. Okay, so they pump it up from the ground underneath them, and when they pump out more water, say the price is very low, so they produce a lot of water, that raises the cost of pumping the water the next period because the water level sunk. Okay, so you got to pump it up further, which means you're going to face a higher cost.
Doesn't the water get replenished at some point?
There's some replenishment, but doesn't fill up it doesn't fill up at the right rate to make it that you can ignore the cost of.
So over the long term, the water is getting lower and lower.
Mm-hmm. Yeah.
Sounds like a problem.
Well, so he's going to have graphs projecting out to 2040. So you would be forced in the optimal problem to, even with their preferences, you'd have to start producing less water in the future. That's part of the optimal solution to the dynamic programming problem. Okay, so once you account for that additional cost, okay, you get even more. That's sort of the marginal cost you ought to be using. Okay, that's what you get from the static calculation. That's what you get from the dynamic calculation, and that's what they're doing. Okay, so these are actually results. There's a whole model that gets us these numbers. These are the actual numbers for that city, municipality. So he's going to estimate this demand function. Okay, for these different cities, he's going to read off these costs and then estimate this dynamic cost from a dynamic programming problem. Okay. And part of that dynamic, so it's the regulator / firm's dynamic programming problem. Part of that is figuring out what are they optimizing to put them there. Okay. Okay, now in terms of magnitudes, you can calculate the static costs in $1984 is about, so once you do the inflation adjustment, we're talking about $50 per resident in 2018 dollars. Okay, this is the data from the 80s. That's for the static, and then the extra dynamic cost is a little bit more than doubles it. Okay, for the city. Okay, so here's the demand function. So how much water is served in city I in period T. He's going to have city dummy variables. The price, this is going to be chosen by the regulator. Okay, that's the control variable. And then he's going to let it vary by the income of the city. So if the city's fortunes are changing over time, this is coming to Eric's point about how much it rained. Okay, this is more on the demand side. Most water, the bulk of it is for watering your lawn and for residential, okay, in California. Okay, the showers and stuff, it's a little bit, but it's really about watering your lawn. Okay, and then he's going to let it vary by the number of residential. He only has residential data, so he's going to assume that the commercial and industrial market is all proportional to the residential market. Okay, so now we got to think about the cost side. So he's going to specify pumping costs and non-pumping costs. Pumping costs depend on the city, okay, some randomness, and the height required to pump the water. Okay, and the law of motion for this is going to have some replenishment built into it. Okay, and the demand. Okay, so if you want to, it's more expensive to pump water. The more you're pumping, and the higher you have to pump it. Okay, then non-pumping costs he just specifies as some city-specific variable with some idiosyncratic unobservable plus times demand. Okay. Okay, so prices are chosen by the municipality. There's nothing that says these are clearing some market or anything, right? It's just a choice variable by the regulator. Okay, so here's how he models the regulator's payoff function. So they're going to have a weight nu on consumer surplus, okay, which you get by integrating the demand function, okay, from observed price up to infinity. And then 1 minus nu goes on to the utilities, the municipal utilities profits. Okay, we want to estimate nu. One of the restrictions here is that nu is constant, the same across cities. Okay, that's different than the French bus paper. Remember the French bus paper, the alpha depended on whether the government was right wing or left wing. Okay, here he's going to say nu is the same across all cities. Okay, so no asymmetric information. Okay, nor commitment problem. It's a single agent problem. Okay. Yes, please.
What is happening on the right hand side? Like 1 minus nu times.
Yes. So this is so this random variable. This is a stochastic disturbance to price. I guess he needs this because his optimal prices he calculates in the model don't always correspond exactly to the prices he in the data. So that's what makes those fit exactly. That's just demand. So this is revenue, and then this is cost. Pumping and non-pumping costs. Yes?
The introduction suggests the regulator not putting too low a weight on the current project, though. Does he expect to estimate the
So closer to 1, yeah, that's the idea. The prices are too low.
Yeah, okay.
Who benefits from low prices? The consumers. Okay, so the idea is that this is not, so maximizing total welfare would have a 0.5 here. Okay, but for whatever reason, and it's not hard to think about the reasons, right? you want to subsidize some parts of your population, and water is very salient, the price of water is very salient, and so on.
We're gonna force that the city with the pricing at zero and the city which is pricing almost marginal cost will have the same unit. And so what will account for it?
Yeah, you have some stochastic shocks here that can, and
They're
then,
gonna account for it?
yeah, and the city dummy variables and the demand function. I mean, it's not, I agree, it seems a little unnatural, but yeah, let me put some stuff in, a little bit in context, and Ariel, we had a discussion after, like this paper was written, it came out in 2002 in econometric, which means it's probably written in like the early 90s or something. I don't know, was it? So, yeah.
I think we hired about 94.
94, and this was a job market paper. Okay, it's a dynamic estimation, nested fixed point, so you got to think about the computational constraints they were facing. So that's part of why you don't have a ton of different parameters and use a dynamic parameter. So I think that's what, if you're doing this with modern computers, you could probably make that more flexible without too much worry. And I agree, it would make sense to do that. And actually wanted to comment about the stuff from the but let me just keep going with this for now. Okay, so that's the dynamic programming problem. Pretty straightforward. Okay. Here's the Bellman equation formulation. Okay, so this is the regulator's problem. The state variables are what's the height of the aquifer underneath the city right now. Okay, and this is an unobserved state variable. It's actually a pretty modern paper in that it had unobserved heterogeneity across cities. Okay, so this is a unobserved state variable that makes different cities different over and above their observables. Here's the law of motion for the aquifer height. Okay, so it depends on the previous period how much you and how much you take out, but it gets replenished. Okay, so this is the recharge rate.
C in this is a demand check,
C is, I remember, no, it doesn't seem to be a, no, it's not on demand. I think it's on, should be here.
right? It says
That's the law of motion for C, but I'm trying to remember, where does it enter? Oh, it's here.
payoff, right?
Yeah. Okay, so what does that make it? It is, well, demand goes through the, I don't know, because demand is here in the consumer surplus. This is 1 minus nu times this. So I guess it means that the firm cares also about, yeah. It's a cost shifter which you didn't write into the profit function for some reason. Yeah. Okay. So I guess, yeah, this is a bit confusing, the presentation. You could think of this being somewhere in one of these components of cost. I guess it would be in the non-pumping costs, right? You'd have a C. Yeah, so we talked about these, so additional restrictions to make this fewer parameters to solve. So the news are constant. The discount rate's also constant across location. That's like fairly standard assumption. And furthermore, he's going to just choose the discount rate to be 0.95. Okay, that's something typical in dynamic models. Well, I should say, so tomorrow we're going to see is the dynamic model session. Okay, so I'm a bit jumping ahead into dynamic models before we really did them. That's just a function of when people are coming and going. So I'm going to, again, not talk about the details of the dynamic estimation. Okay, but one thing that's typical is and there's reasons for this, is that the people just set the beta, the discount rate, at something that's either 0.95 or 0.93 or something like that. Okay, so yes?
I might be missing something. If this is the objective function, I still don't understand why the result would be pricing below marginal cost. Suppose he was interested just in consumer surplus. you would still not price below marginal cost. Now, if someone is paying for it, the people who are paying for that are the citizens of the city. Who's paying for the cost of pumping? It's the citizens of the city.
Yeah, but then
So
they're not all
if you want-
taxed.
If you want to, if you want to be efficient, then you want to set the price at the marginal cost. So that someone who derives a value that is less than the cost will not do that.
Okay, so I see what you're saying. The money that the city raises to pay
Yeah.
is not taxed equally from everybody. So there's distributional reasons why you might let the price of water be low and let the rich people pay for the pumping costs.
After that, so the guy is being elected, or appointed by an elected official. Okay, they attribute to this guy the price of water. They don't attribute to him taxes. They attribute that to a more broad thing. So the guy has, when the price of water goes up, the guy who's in charge of water gets hit in the newspaper. But when taxes go up, somebody else gets hit in the newspaper. So that's what's going on. I think.
But I think also
But then that doesn't correspond to the objective function he had.
It
I
does.
mean, he probably has some other. I don't
so the progressivity of the tax system matters here, right? Because that's not the distribution effect. There are distributional
That's
effects.
reflected in the objective function.
It's going to be baked into the value of new. So if you get a new that gets you to price less than cost, that means you have opinions on the distribution of income.
Or you care about being elected.
So imagine my opinion on the distribution of income is I think rich people should be taxed a lot more and have to pay more for everything. Okay, one way to, if I have a tax system that taxes rich more, I can aid my objective by giving water away for free and then having paying for it through the tax system.
But another way is to price water efficiently and have a progressive tax, or even a negative tax.
I agree, but at the end of the day, we see the price way below marginal costs. So we see the price way below marginal costs. So we're going to think about,
So there's some restriction on what the town can do. They can't use an optimal tax scheme for some reason.
yes,
Okay.
yeah, which I don't think is that crazy of an assumption to maintain. Yeah.
But
Yeah.
so there are different actors making different decisions. One, neither of them have optimality in consideration. One wants to get elected. And the way he gets elected is he has low prices of water. He's elected separately than the mayor who sets tax rates. Well, I don't know who sets tax rates, but whoever sets.
Well, that's not optimal either.
Yeah.
Nobody said it was optimal. We're trying to describe the world.
This does assume some optimization. Okay? I mean, the model does assume an optimization.
Right.
So the question is what is being.
I agree. So if we want to do
what
income
is being
redistribution,
optimized here, because, I don't know.
well, no, it's clear what's being optimized, right? The optimization problem's well defined. Okay, what you're objecting to is you think that this value should be 0.5, and he's
I'm
gonna t-
probably missing something. I'm saying that if you were interested, if you were just looking at consumer surplus minus cost, you would not price below marginal cost.
Yes, but
Price.
so what
You would
implicit-
price at marginal cost.
implicit in
You
that
don't want a
statement-
consumer who gets a value that is less than marginal cost to consume the water.
so implicit in that statement is that new is 0.5. Okay, and what he's going to do is measure new from the data. It could come out to be 0.5. Okay, if it's greater than 0.5, that's going to get you prices below marginal cost. Okay, now you can ask, so it seems like you're saying, I don't believe any new, any estimation that gives me a new that does not equal 0.5. And again, I think it's like a very strong opinion to have given the complexity of the situation. Okay, so the estimation is complicated by that unobserved heterogeneity term. Okay, yes, there a two-step nested fixed point algorithm. Hopefully this will get discuss in the next few days. But one easy to understand detail, and it's very common in dynamic models, is that you can estimate a bunch of the parameters, like of the demand system and cost system, what's called offline. Okay, that means without solving the dynamic program over and over. Okay, so a typical way to estimate the parameters of this model would be guess a set of parameters, solve the dynamic programming problem, compare what comes out of the dynamic programming problem to what's in the data, okay, and try to make those things close to each other. Okay, but that's a lot of parameters, and the dynamic programming problem takes a lot of time to solve. Okay, so that's computationally difficult the more parameters you have. Okay, so what you can do is a bunch of the parameters, like on the demand and cost side, don't really depend on the dynamic programming. You don't need them to identify those. Okay, you can do them with regressions or something similar. Okay, so that makes it a lot easier. So here are the parameters estimated offline. They're demand, lift height, law of motion, right? You can just sort of do a regression there, pumping costs and non-pumping costs. Okay. And for demand, you'd probably want an IV rather than a straight linear regression, but it's still way easier than doing the full dynamic programming problem. Okay, so that gives you the dynamic parameters. Okay, so we set beta at 0.95, and we have to estimate nu. So we're estimating a nu of 0.73 rather than 0.5. Okay, and you can actually squarely reject 0.5. So this is the variance of Cassie, and these are the Cassie law of motion parameters. Okay, so that's the result. It's kind of straightforward. The prices are lower than marginal costs because in this model, the way to interpret that is regulators are putting more than half the weight on consumer surplus. Okay, so I think it's a fair position to say, well, why would a regulator ever do that? Okay, but I don't think it's too much of a stretch to come up with reasons like opinions on income distribution and rigidity in changing the tax system to get that. Yep.
The standard error on new is very, very small.
Mm-hmm.
So this is kind of by construction, right? Because we're soaking up almost all the difference in a lot of stochastic terms.
I think that's a fair point. And coming to your earlier point that if new varied by city, you'd have more parameters, and each one would be a little bit noisier than having one single one. Yeah. Yeah. With that.
Like it would be interesting to see what happens because, like, you're telling me so nu is 0.73 and it's perfectly estimated. So now we all should believe that nu is, but we won't. So
yeah, I think that's exactly the right attitude to have. Yeah. So in the context of the model, it's correct, but then we take a step back and think about what does it really mean, and you also got to appreciate the computational considerations that were being faced at the time. Yeah, yeah it's good. Okay, so we get all those parameters. What are we going to do with them? Well, he's going to do some counterfactuals. So he's projecting out to 2040s. This was in 1990. Okay, so it's going to be noisy, right? Just when you think about it. Okay, so continued current behavior. So these are the price paths. Okay, so the current behaviors, you got low prices. Okay, and if you continue at current behavior, he's predicting that you keep getting low prices, but eventually the thing kicked in where you have no water left in the ground, and you're going to have to start conserving with higher prices. Here we have the static optimization. So that's how you would price water were you not to think about the effect on lowering the aquifer height. Okay, and this is the dynamic consideration. Okay, so when you do the whole problem. Okay, so prices are quite a bit lower than what would be optimal, even using just the static. Like this is not that difficult to figure out. Okay, for a regulator. Okay, so you might say, well, why aren't they doing this? So this is maybe a little bit more difficult dynamic program. Okay, this is not that difficult. Either way, you're sort of off by a good chunk. Okay, what would be optimal? So this is the punchline of the paper. Okay, and it kind of, and we'll see this pattern in another paper, the Ryan paper later. Kind of starts from a very sort of simple empirical observation that prices are way below reported cost, and then all the dynamics sort of really makes you feel comfortable that you've crossed the T's and dotted the I's and taken everything into account. Yes.
So you have to fix the discount rate so you can't estimate it. There's presumably some discount rate under which the current behavior is optimal. So you might have just picked the wrong.
I'm not, well, okay, so the question is there a discount rate under which this price path is optimal?
You just put a very high weight on your current consumption and don't worry about the future at all.
Even then, right, then you'd use,
After the cost is still nothing.
yeah, then you'd use this, I think. Something like this. Yeah. You'd price at marginal cost in that period.
Do we see time trends like before?
What do you mean, do we see?
Like, did you show us like what happened?
No,
What's the type price trend before?
It's not in, it's not in the paper. Yeah, that's a good question. So the question is,
Because this is all the first data point here is the last data point we have. So
Yeah.
we can't estimate better from this.
right. The question is, what does the actual data look like for the actual price path? Like, what does this look like? I'm pretty sure it wasn't in the paper. I like that. That's a good. I'd be interested myself to see that. Yeah.
I wonder if this kind of exercise, if solving the dynamic problem for a finite amount of periods should be easier, would be a reasonable approximation to the infinite problem.
Okay, so the question is, if we set it up as a finite horizon problem, some capital T, like T equals, I don't know, 20 or something, is that an easier computational problem? I don't know. The infinite horizon often makes it easier because you get the Bellman equation formulation. So I'm not sure. I don't think so. No, that's the, yeah. In a stationary environment, I think it's usually easier with the infinite horizon.
So now if we look back, if we can
Yeah, it's a good question.
test his prediction.
Yeah, I don't know if anyone's
Yeah.
done that. I'd like to see that too. Yeah.
Going back to the question that was asked here, if it seems that there are political considerations,
Mhm.
then one would think that the discount factor would be far, far lower than 0.95,
Mhm.
because you would expect someone who makes a political consideration to really carry.
I think that's a good point. Ari, you want to add to that?
Yeah, he has the subsequent paper does that. So he puts it on, the voting years are different from non-voting years, and he adds that to the thing. I think here he would have done the news separately also, it's just that at that time computation, now he could do it easily. I mean, just computers are such that it would be trivial. But then he couldn't do it.
Yeah.
And he might get standard errors that are larger. But
Yeah. No, I think it's just to repeat it, it's a good point. So there it's sort of obviously political, right? It's about firms and consumers and taxes and stuff. And the point is, could political considerations also make regulators behave with a different discount rate than like what they could borrow at on a open market? And I think that's a good point. Yeah, it could be. So Ariel was saying, I don't know, there's a follow-up paper which makes new depend on,
no, it makes beta change.
oh, it makes beta change?
Beta
Okay.
change.
Because you could also make new depend on,
Yeah.
yeah. Okay, so I don't know that paper, but yeah. Okay. Okay, great. So let's move on to the next one. This is a paper I wrote with Claire Lim. It's in the JP. It's back to regulator utility multi-agent problem. Let me say, so now let me pause here about the previous one. If you went away from that sort of being a little bit empirically unsatisfied with the answer, I think that's a bit healthy. And less so on the last paper, to be honest, but on the first three, because these are like pretty simple approximations to very complex environments, and the data is very noisily measured. You'll see that here as well. My mandate was to tell you what's in the regulation literature. I think these are the best papers, but there's still a lot of work to be done. Okay. Okay, so what I'm going to show you, if you want to place it in the literature, think of it as like a multi-agent Timmins / dynamic Wolak paper. Okay, and this multi-agent nature of the dynamics is going to lead to an issue of time inconsistency. Okay, all right. So with Abito, we were here. Okay, now we're over here. These are the power lines you see on the street in the U.S. Okay, that deliver power to the home. Okay, most power outages are because of here. Very few of them. We're talking like 90% of power outages are because of issues here in the U.S. Okay, very rarely will there be a power outage because of something here or there. There's the California blackouts, which were about here. They were very famous, but it's a minority of power outages come from that. Okay, large minority, or small minority. Okay, so these are the types of behaviors and the capital that these firms are investing in and maintaining. Okay, they're trimming back trees, fixing power lines with these bucket trucks. These are owned by the firms. They're planning their system. Okay, there's a complex electrical engineering problem on where to put the different substations and what type of lines to put. Okay, when to replace transformers, and so on. Okay, that's the business of these firms. Okay, and it's largely responsible for power outages. Okay, so I mentioned this the other day. This is my neighborhood. It's a picture from my car, Redwood City, California. It's a beautiful setting. You know, weather's nice, rolling hills. Okay, but everywhere you go, you look up, this is what it looks like. Okay, so now, in terms of power outages, it's not so bad because the weather is nice here. Okay, so it's not that, you know, this one is sort of isolated from trees, but there's parts where like, there'll be a big tree just sort of sitting here. Okay, and if there were thunder, or lightning, which there rarely is, okay, it would take out the system. Okay. Now, one extra point, which is not going to be in the paper, which I think is legitimate. There's an aesthetic improvement to burying these also that raises house values, but we don't know by how much. Okay, it bugs me though. Okay. Now, but in terms of power outages, here's power outages for the U.S. The measure people use in this world is called the SAIDI. Okay, it's the System Average Interruption Duration Index. Okay, what it measures is basically how many minutes per year are you not having power. Okay, and in the U.S. the average is about up to 2010, 2011, 141 minutes per year. Okay, so it's not a huge fraction of the year, but think about it as some probability of having your power out for like 8 hours or 12 hours. Okay, and that's the average, yeah.
Some of those scheduled to be during the night or during off hours?
Yes, those are not counted in this, and this is also further excluding major events. Those are events where the outage is more than 3 standard deviations duration than the mean. Okay, so like Hurricane Katrina is not in here. Although arguably it ought to be. Yeah. But it makes this thing very variable. Okay, so for regulatory purposes, they use excluding major events. Okay, so the time trend you can't really interpret because the people didn't really measure this much many years ago. Okay, so there's a time trend, but there's a compositional problem. So we can't interpret that much from the time trend here. You can compare it to other countries. So this is, and of course that comparison comes with, a lot of stuff is changing from country to country. Right? Okay, but comparing to Europe, so France and Germany are here. Okay, we're looking 5, 10 minutes, 15 minutes per year. Okay. US is this black line. Okay, so the peer countries would be like Portugal, Greece. Okay, it's not as bad as Turkey, but it's getting close. Bulgaria. Okay, so there's a sense, I think there's a sense that, now, okay, US is less dense than Europe, it's more variable weather in parts. Okay, so it's not an apples to apples comparison. Okay, but it seemed a bit high when I saw it. Okay, more than I would have guessed the difference. Okay, but what we can do is, what we're going to come back and do is make the calculation, and we're going to measure the costs and benefits of how much do basically firms say they lose from power outages, and we're going to estimate how much it costs to reduce power outages. We're going to do that comparison, and we're going to find the U.S. It looks like they ought to have fewer power outages. Okay, so this is just more suggested. Okay, so that's the first thing we're going to do. We're going to do that sort of empirical investigation into the costs and benefits of investing in capital to reduce power outages. Okay. With that in hand, we're going to look at some empirical relationships between, these are regulated utilities. Okay. We're going to look at how their rates of return and also a measure of static productivity, which is how much electricity is lost when it's getting, to deliver electricity from one place to another, some gets lost along the way. Okay, that's waste, and firms have some control over that. Okay, we're going to look at how those two things vary with the political leanings of the regulators. Okay, it's going to be a left-wing, right-wing thing. Okay, and that's going to be, we're going to see some patterns in both of those that are going to form the basis for estimating the dynamic regulator utility game. Okay, and in that, when you write down the dynamic regulator utility game and you use a Markov perfect equilibrium, which is what's going to be taught in subsequent days, there's a time inconsistency dynamic. Okay, exactly what I was talking about a few days ago is that you want the firm to make investments to reduce power outages. Okay, but because the regulator controls the price in the future, once that capital's sunk, okay, the regulator is tempted to reduce the rates. Okay, and if they can't commit to a path of rates, that means you're going to get too little investment. Not zero investment, but too little. Okay, so we're going to get that dynamic, okay, and we're going to see that it differs depending on the political leanings of the regulator, okay, how severe it is, and then we're going to simulate regulatory commitment.
How are you going to get the winners to pay for reducing power outages?
It's survey based. Yeah.
So,
Yeah. But we're going to do robustness to that level because that's going to be one of the caveats. Okay. Yep.
Does the regulator charge them a fine when there's no power?
Not unless it's something egregious that the utility ought to have fixed. Okay, so they just say it's part of the normal. The power outages, you're not going to stop all of them. So it's just part of the course of business. Now what they can do is give you, if they could commit to high returns, that would give you an incentive to invest in capital to reduce power outages. But you don't have to pay a fine if you have a power outage.
Was there ever a class action against the utilities for this?
No, I mean, well, why would there be? They're not doing anything wrong necessarily.
They're underinvesting and causing loss of income to consumers.
But they're not, I mean, they don't get, if they're worried about not getting paid for their investment, you can't blame them for it.
I can try.
I don't know how, I don't think it's,
Okay.
yeah. Okay, so when we, let me just give you, yeah, please.
I don't want to keep you, but it resembles a little bit computer games with imperfect monitoring. Okay, and then when you see something bad, you don't know whether it's the fault of a player or not. Then what you have there is that you still punish.
Okay,
And
so
that provides incentives, and that would seem to get around the issue of commitment that you were talking to.
okay, so
Because he knows that he's going to be punished in case there is a problem.
okay, so the question/comment was, this resembles a model of repeated interaction with imperfect monitoring, and part of the equilibrium to those games is that there is a punishment in sort of low output or low quality time periods, and that equilibrium, I guess the implications would solve the commitment problem. Yeah. Okay.
You don't see it.
Yeah, right. That's so.
don't see-
I think it's a fair question to say, like that's a counterfactual one could run. Is what if you, what if you set up the regulatory process to mimic the types of solutions you get from that problem? Okay. Yes.
do you know to identify whether those shutdowns are like net or network derived, or is it from the producing, like electricity producing?
Yeah, so when they've made these calculations, it's 90+% are coming from the distribution network. Okay, so think of,
Consider like a monopoly, right?
it's a natural monopoly. Yeah.
You can have another electricity producer, but it's much harder to add another like distributor.
That's right. We only see, okay, there's one town in Texas that has 2 electricity distributors. In the US, it's always one, yeah. So that's why they're regulated. Yeah. Okay, so that's the idea. So we're going to do this measurement, which is, it's a bit spotty, but we'll do robustness with respect to the assumptions here that the value of reducing outages is large relative to the cost of doing it. So it seems like they're not doing enough of that. Okay, and we're going to explain by the lack of regulatory commitment. Okay, and this is, again, I mentioned this is the reverse average Johnson effect. Average Johnson is that undergraduate model of regulatory behavior where the implication is that firms invest too much. They gold plate, okay, as they get some return on investment, so they just want to keep investing to get more returns. Okay, so this is a quote from a handbook by Joska, who has a bunch of nice papers in this area, handbook chapters and so on. Okay, so what he says is, he sort of raises the question, will the possibility of ex post opportunism or regulatory expropriation, that is reducing the rates after the investment's been made, okay, perhaps driven by the capture of the regulator by other interest groups, like, regulatory capture doesn't have to be just by firms, it could be consumers capture the regulator. Like in Timmins, that's effectively regulatory capture by the consumers. Affect its willingness to invest in the lowest cost technologies, okay, when they involve more significant sunk cost commitments, okay, leading to the opposite of the AJ effect. Okay, that's the idea here. Okay. So this is, each color here corresponds to a different monopoly territory for a different utility. Okay, some of these colors cross lines, and when they cross lines, it's a different company operating. Okay, so down here, this is Southern Electric. They have an Alabama Electric, a Mississippi Electric, and a Georgia Power, and they also have something in Florida, Gulf Power or something like that. Okay, so those are 4 different companies under the same holding company subject to the regulation of that state. So you have holding companies which cross state lines. You also have within states, you can have many different electricity distributors. Okay, and the places you see white are, okay, one of 3 things. Either the city or the state runs the electricity distribution network, like how in Timmins the city ran the water network, or it's a cooperative, the customers own it. Okay, and in Tennessee it's actually federally run. Okay, that's the Tennessee Valley Authority. Okay, so recall from Abito, what you're trying to, you have these rate cases every few years. They're trying to figure out the revenue requirement. Okay, Abito is really focused on the costs. Here the focus is going to be on the return on capital. Okay, that gets awarded to the utility. Okay, now a little bit more on this process is they go through the procedure. They come up with a draft document, okay, and that gets voted on by the commissioners of the State Utility Commission, of which there's typically 3 or 5. Okay, typically appointed by the governor of the state. There's a few Western states where they elect them. Okay, but all the big, the New Yorks and Californias, Illinois, Texas, they're appointed by the governor. Okay, and the terms are roughly 5 years. Okay, every state's a little bit different, whether it's 3 or 5, and the terms and so on. Okay, so our data. One nice thing about regulated industries is you get a lot of data because they measure so many different things. Okay, so for each utility company, we can see their reported capital for the distribution. Okay. Some of these companies are also involved in transmission and generation. Okay, but this splits it out by distribution. And we can also see how much energy they're losing in delivery. Okay, so this is like a measure of productivity. How much waste? Okay, so to deliver 1 unit there, how many units do I have to procure? Okay, and the smaller that is, the more efficient my delivery is. We can see the approved returns, okay, for each rate case, going back a decent amount. Then we, with the help of a company and a bunch of work by ourselves, we assembled a database of duration and frequency, okay, of power interruptions. This, since 2013, is collected at the federal level. Okay, so the data after 2013 is really nice here. Okay, but going back to the 90s, it wasn't great. Okay, so it's noisily measured and so on. Okay, then we're gonna condition on a bunch of stuff like how bad the weather was. If you have lightning and so on. Population density is very important, okay, and income. Then on the politics side, what we have is the party affiliation of each regulator, of each commissioner. Okay, so it'll be like 5 commissioners, maybe 4 Democrats, 1's Republican in one state time period, and another state time period, two Democrats, 3 Republicans. That'll let us do. We also collected data on where did they come from, like were they lawyers or in the energy industry. We ended up not using that. We didn't see much there. This is going to give us within state over time variation in the regulatory, in the politics. We're also going to do some cross-state comparisons. Okay, comparing. You can basically look at who does the state vote for in presidential elections and say that's how Republican or Democrat that state is. Okay. All right. Okay, so coming in, Nikhil asked earlier, where do you get this? We don't pay on the margin to improve our quality, right? I can't get like a higher electricity package with better reliability, so it's hard to measure taste for reliability. Okay, so but they need to make decisions about how much to invest. Okay, so what's done is they go out and they run surveys. Okay, and these are better than the surveys of like where you ask consumers how much are you willing to pay for a national park that they've never been to and are never going to go to. Okay, which that's an issue. Okay, these are like they take a random sample of firms, they send someone there who's knowledgeable, they sit down with the management for the day. Okay, for restaurants, they ask like, how much spoilage would you have from an hour, from 2 hours? It's pretty detailed. Okay, so it's not. There's a real effort being made, and they split it out by large, medium, and large commercial industrial, small commercial industrial. So these would be like retail stores that got to shut down and pay, but they still got to pay their employees, but they can't sell anything. These would be like factories who got to shut down and might have spoilage, or their machine might break because of the power outage. And these are houses. Okay, the first order thing is that you can basically ignore the houses. Okay, it's all about firms. Okay, hospitals. Okay, hospitals, they have generators. It's not like everything shuts down, but the generators or backup generators are costly. Okay. Okay, so this is our valuation data. Okay, and we're gonna scale this up and down, actually mostly down. Okay, if we're worried about it overstating. Okay, you might try to think of what are the incentives of the firm to report truthfully here. It's not that they want to report too high of a valuation because they have to pay for the electricity. They're going to pay for it in the price. Okay, so it's not clear what the incentives are. I think it might even be incentivized to tell the truth here. Because say they say it's extremely costly for us to have a outage, with the hopes that they're going to make the electricity company invest a lot in reducing outages.
What do they expect that will happen on the basis of this?
Well, the purpose of this is to figure out how much investment ought to be made.
So this is an input to the rate regulation and investment process?
Yes.
Okay.
Mm-hmm. But if they give a really high number that's higher than their actual value, they're going to end up paying for it. Yeah. Yes?
You mentioned generators. Does this include ongoing mitigation costs or insurance, other risk costs?
Yeah.
Because it's unreliable?
Mm-hmm. Okay, so the question is what's the set of costs that go in here, and so ongoing mitigation, you mean actually running the generator?
The fact that they might have interruptions might make them buy a generator. Is that a cost of interruption?
Yeah.
Or they might not have a cost of interruption because they bought a generator, but of course in equilibrium, if the service got better, they might not have to bought the generator.
Right. Okay, so 2 answers. One is even if they have a generator, that fuel cost is expensive to run the thing, so there is a cost there. And the second is this is an average across many different surveys, about 30 different surveys, and there's some variation in what they count and what they don't count. I think some of them don't actually count the generator cost. Yes?
When you say they have an incentive to underreport, does the electricity company can charge different consumers at different rates?
They charge different consumer groups different rates, like commercial.
If you're on a single firm, my report would not change how much they charge for all the firms.
If you're chosen, it's like they're running a survey from a sample of firms. You're one of the firms in that sample, so you might have a small effect. It sort of depends. But yeah. if you're the only firm they surveyed, I don't think you'd have an incentive to over or under
The
report.
government allows them to discriminate in any way between firms and consumers?
No, that's part of the rate case. So the outcome of the rate case is not just a single price, it's a price for commercial, price for industrial, and price for residential. Okay? And it's not just a single price, it's actually a nonlinear schedule. Okay? Okay, so that's the citation for that. It's 28 customer surveys. Okay, the surveys take about 2 to 4 hours. They do. Another place that this gets surveyed is in when they're thinking about electricity capacity markets. There's this thing called the value of lost load. Okay, these numbers we get from here are a bit higher than those numbers there, even though they should be measuring the same thing. Okay, but these numbers are what get floated around in distribution circles. Okay, so that's the benefit side. What we do here is we're now going to regress power outages, minutes of power outage on how much capital you have. Okay, so think of this as the right-hand side is a dollar number. That's how they do the accounting for capital. Okay, so say you installed a bunch of power lines, you put that in there at the cost you paid, get depreciated every year. Okay, so different things are being depreciated every year, and they form this aggregate capital measure. Okay, so it's a pretty noisy measure of, if you tried, it should be something like how much would it cost you to recreate the distribution network you have if you were to build it from scratch, the capital cost of that. Okay, this is not quite that, but it is a measure of sort of how much investment they've made. Okay, so focusing on this specification where we control for weather, we have fixed effects, and we use log. Okay, we get an elasticity of about minus 0.5. Okay, so 10% increase in distribution should reduce power outages by about 5%. Okay, minutes down. Okay, so then you can do the following calculation. This is back of the envelope. The model is going to do this more carefully. Okay, you can say at the mid-range of these valuations, and mid-range means because people report for different durations, we're going to take not the extreme, but something in the middle. Okay. An average customer, that is when you take the fraction of industrial, fraction of commercial, and fraction of residential and get the average, okay, values 1 minute of improved reliability of about $250 per year. Okay, so that gives you a net present value around $60. Okay. And from these regressions, we get the estimated cost of improving reliability by about 1 minute at the mean capital level. Okay, that's about $26. Okay, so that means if you're optimizing, you ought to invest more. Okay, to equalize these. But we don't see that, so that's what we're going to say is evidence of underinvestment. Okay. Okay. Now the model is going to do this calculation in a more detailed way. We're going to account for depreciation. Okay, the fact that there's investments in the future, regulators change over time, and so on. Okay. Okay. So some caveats. One thing we don't know, we only see the outage measure for the average customer. We don't know that if within a territory the utilities targeted the reliability at the industrial customers, like if they really bulwarked around the hospital or not. Okay, because that would change the calculation. Okay, because the hospitals are the ones who really value reliability. We're saying something pretty strong. We're saying that they're massively investing in reducing power outages, okay, by looking at sort of these comparing these averages and. Yeah.
Does the firm do the surveys, or does the city do the surveys? Does the authority do the firm?
It's a mix. You get both types. Yeah.
Because the firm should know, if it did the survey, it should know where the marginal productivity is highest.
Yeah, they do. Yeah, I mean they know hospitals and strip malls and that sort of thing is where the money is. Yeah, factories. Some special factories will strike deals with the distribution code. That we know, it does happen a bit. Yeah. But those are ones where like the equipment is even sensitive to the frequency that the it's a very specialized thing. Yeah. Okay. Okay, but I mean this is This is a big part of the paper. It's also a big caveat of the paper that, it's all about how good are these. It's really, this number we can argue about. At least it's coming from some real measured data. These are the survey measures. Okay, so if you don't believe that, on the other hand, if you scale it down by a half, it still indicates mismeasurement, underinvestment. Okay. I'm going to have to go a little bit faster. Caveats. Okay, there's other issues. I mentioned the capital measure is noisy. Okay, now we're going to do a little bit more empirical analysis. What we're going to look at is, on the left-hand side, we're going to look at either the rates that are being granted, okay, the return on the capital base. This will be a number like 6%, 8%. Okay. And then we're also going to look at that measure of technical efficiency, how much energy is being lost in the delivery. Okay, and the variables on the right-hand side that we're focused on are political variables. So we're asking, when the fraction of Republicans on the commission gets larger, do we see higher regulated rates, and do we see different technical line losses? Okay, and then we're also here, that's within state over time. So we have utility fixed effects and time effects. Okay, so I'll tell you about the variation here. And we're also going to do a bit of cross-utility comparing Republican states and Democrat states. But that's a bit harder because the terrain differs a lot. Okay, so these are the 10 most Democrat states based on how they voted in the presidential election, the 10 most Republican states. Okay, and then for each state you have, across the 20 odd years in the data, the minimum fraction of Republicans on the commission and the maximum fraction. Okay, so there were years in Massachusetts that all the commissioners were Democrats and years that all the commissioners were Republican. Okay. Now, in Vermont, there was never a year that all the commissioners weren't Democrats. Okay, Maine the same. Okay, but you do have variation like that. Okay, here's one state. This is Michigan. Okay, so you had a Republican governor for about a decade. He kept some Democrats on the commission. Who knows? It's wheeling and dealing. Okay, and then some of them left, and it went to all Republicans. Okay. Democrat governor comes in, okay, and then this is their terms expiring, appointing Democrats until there were all Democrats. Okay, then she was no longer governor, and the new governor was a Republican, and starts ticking up.
Party ID does not track ideology very well, especially in some southern states in the early part of history, like in Texas, and then kind of Democrats left over from the Civil War.
Yeah.
So what, the state fixed effect will pick that up?
No, it won't, because that's varying within state over time.
Right.
So this is a bit in the weeds, but what it means to be a Democrat or Republican is different in different states.
Yeah.
And particularly there was a reclassification in the 80s and 90s where Southern Democrats all en masse became Republican. Okay, so we're going to be a little bit after that. Okay, but you should keep that in mind. Yeah. Okay. So the average return on the capital base is about 9. Okay, they split that into how much you can give to your equity holders versus your bond holders. I'm not going to get into all that. We're going to focus on the equity holders. That's where the most discretion is. And then this is a histogram of technical efficiency. Okay, so the average is about 0.93. That means you're losing about 7% of the electricity from when you procure it to when you deliver it. Okay, but you can see some places lose less, some places lose more. Okay, in dollars, this turns out to be about $15 billion per year just evaporating through the system. Okay, so here in this table, the right-hand side is the return on equity. Let's focus, and this actually relates to your point. Okay, let's focus on the within utility regression. So here, all the variation, it's not about comparing different states, it's all as the commission turns over. Okay, and what we see is you look after the whole period, we don't actually get a precise estimate. It could be fairly positive, could be fairly negative. Okay, but as you go up in time, you see that so if you cut off the lower years, you see a stronger and stronger correlation of rates with partisanship, and that's consistent with sort of increasing polarization. It used to be Democrats and Republicans were less different than they are now. Okay, and you also see it across state, okay, which is going to be, we condition on demographics and stuff, but that's a dicier comparison. Now, on the technical efficiency, we also see that the fraction of Republicans is associated with higher line losses. Okay, this is saying in utility years where more of your commissioners are Republican, okay, we see less technical efficiency. Okay, and the model is gonna rationalize all that through the alpha parameter. Okay, the basic idea is if you put a lot of weight on the firm's profits, okay, then you're going to pass through their costs more, which gives them less incentive to exert effort to be efficient. Okay, that's part of the Baron-Meyerson solution. Right? If alpha equals 1 in the Baron-Meyerson thing, it's like it's full information. You let them just report whatever cost they want. Okay, so we have a few patterns now. We got some evidence of underinvestment in capital, sort of across the board, or on average. Evidence that more conservative regulators goes with higher returns, and evidence that more conservative regulators goes with more energy losses. Okay, so now that's all gonna fit into this dynamic game. Okay, so there's infinite horizon, discrete time, two agents, the regulator and the utility. Okay, the state space is going to be a capital base of the utility, and then the regulator's weight, the alpha, is going to be evolving because of elections and stuff, right? Like in Michigan, it was changing. Okay, that's going to be a state variable. Okay. The actions that are going to be taken within period, the utility is going to choose how much to invest in capital and how much effort to exert to reduce line losses. And the regulator is going to choose how much of a return on capital to offer to regulate and how much cost to pass through. Okay. So if they could commit to a really high return on capital going forward, you'd get a lot of investment. Okay. If they pass through all the costs, then there's no reason to exert managerial effort, right? Because you just get reimbursed for it. A regulator who's tougher on the utility is going to grant lower returns and pass through less costs. Okay, so a regulator that's tougher on the easier on the utility, more lax, is going to give high returns and pass through a lot of costs. Okay, so you can see where this is going. The alpha is going to be positively correlated. They're going to put more weight. The conservative regulators are putting more weight on profits relative to Democrat regulators in this model. Okay, so it's one parameter that explains both of those patterns. Okay. Okay, so the demand system, it's going to be similar. So it's going to be inelastic up to a choke price. We're talking about electricity. So the idea is that in the short run, you can't really change your electricity demand too much, how much you consume. How much you're willing to pay for it is going to depend on how much capital the utility is installed relative to how many customers it has to serve. Okay, this is the value for reliability. Okay, I'm more willing to pay for my electricity if it's going to be more reliable. Okay, and we're going to calibrate beta to match the survey data. Okay, beta tells you, so this is data, this is data. Okay, beta tells you how much I value an additional minute one less minute of power outage. Okay, and we have the surveys that let us calibrate that. Okay. Okay, so here's the profit function for the utility. The revenue, that's P times Q. So P is not chosen by the firm. Okay, P is a function of is effectively chosen by the regulator as a function of other choices by the firm. Okay, so that's sort of, we'll come back to that. They get to decide how much to invest, and there's some depreciation, okay, in their capital base. And we have a quadratic adjustment costs of investment as well. Okay, that makes the problem well behaved. It's fairly typical. Some of these are, it's not atypical in dynamic investment models. So it makes gives a concavity to the optimization problem. This is the cost of procuring energy. Okay, they got to buy the energy. Now, by exerting effort, okay, they reduce how much energy they have to buy to deliver a certain amount. Okay, so effort, if you exert more effort, you reduce your procurement costs. Okay, those are the technical line losses. Okay, and that's the effort cost function. Okay, then there's an idiosyncratic level for shock to each utility in each period. Okay, so utility has two choice variables. They're going to choose E and they're going to choose investment, this difference. Yep. Okay, now the regulator, the other player in the game, they choose a rate of return on capital and how much of the procurement cost to pass through directly. Okay. So that's R, and that is a coefficient on the energy loss, kappa. Okay, once the utility's made its decisions on investment and effort, and the regulator's made its decisions on R and kappa, okay, that's how much revenue the firm needs. That's the revenue requirement, right? This is revenue equals return on capital base times capital plus operating costs. Okay, so in terms of what we were talking about earlier, this is more similar to the Abito style thing where we're not assuming the optimal mechanisms being employed by the regulator. Okay. Where we say the regulator is maximizing, this is like in Timmins, is some weighted average. Here we're using a geometric average of expected discounted consumer value and the firm value function. Okay. With weights alpha, where we let alpha depend on what fraction of the commissioners are Republican and how Republican the state is. Okay, so there's some, do some algebra, simplify things a bit. It's a dynamic game. Okay, so both the regulator and the utility have dynamic problems that have to be solved in equilibrium with each other. Okay, I'm going to tell you what the definition of an equilibrium is here. You're going to get a lot more detail on this stuff in the next few days. Okay, we're going to consider a Markov perfect equilibrium, okay, which is going to consist of policy functions for the utility. So it says as a function of the state variables, how much do they invest and how much effort do they exert. Policy functions for the regulator, so as a function of the state variables, how much rate of return do they adjudicate and how much cost pass do they let through. Okay. And associated value functions, one for the utility and one for consumers. Okay, and those two together give you the regulator's value function. Okay. Such that the utility policies are optimal given the regulator policies and their value function. The regulator policies are optimal given the utility policies and both the consumer value function and the firm value function, which forms the regulator value function. Okay, and the utility value function is implied. Each value function is implied by the policies. Okay, so everything is consistent with each other. Okay. So one comparative static in this model is that if you put more weight on utility profits, you're going to grant higher returns. Okay, because you like the utility, you give them more money. Because that money is contingent on how much they invest more. Okay, and if you like the utility, you're also going to let them pass more of those costs to you. So you don't worry about the electricity loss. We'll give it to you. Okay, so you're going to get more energy losses. Okay. So that's what's going to, because we see these in the data associated with more conservative regulators. Okay, whoops. We're going to get that these move in a way that more Republicans put more weight on, so less weight on consumer value, more weight on the firm value.
But the firms like high rate of return, right?
Yes.
So you get that the Republicans give them low rate of return,
No, Republicans are going to give higher rates of return, like we see in the data.
but then they should invest more.
Yes.
They invest more.
Yes. That's the idea. Yep. Yeah. So Republicanness is going to be a defense against the time inconsistency problem.
So if they
Not because they care about future reliability, just because they like the utility.
Yeah, so if they invest more, they have less shortages.
Yep.
But we see that during Republicans, we have more shortages.
No, we see more technical line losses. So those two things are different.
And less shortages? I missed that.
I didn't show you the shortage numbers. It's noisy.
Okay.
Yeah, so that it would be nice if we saw that, but it's noisy. Yeah. We see a little bit more investment. Okay, so there's two other papers I want to cover. You get the policy functions. Okay, they have those comparative statics. Okay, again, I just want to point out that recall the caveats. Like a lot of this turns on measuring the value of reliability well. Okay, and we got to do robustness to that, and we do. Okay, so you get that Republicans put less weight on consumer surplus. Okay. Some quantification. Let me get to the counterfactual that we're interested in. Okay, so moving from the baseline. Okay, so this is what we sort of estimate's going on for the average utility currently. We consider a counterfactual where we have a full commitment. Okay, so here the utility moves first, chooses a policy function. It's like a Stackelberg game. Okay, then the utility responds. Regulator chooses the policy function, then the utility responds. Okay, so it's like a Stackelberg game. And here we just say, well, what if all regulators have the alpha of the most conservative state? Okay. So the full commitment is going to lead to higher returns on capital, okay, by a little bit, about a percentage point, okay, which is going to feed into getting more investment. Now, here it's going to look like investment went down, but what's going on is actually you are spending more time in the high capital states where you invest less. Okay, so this is mixing two things. If you just look at the investment policy function, that goes up a lot. Okay, so for a given state of the world, people invest more. That pushes them into higher capital states where they then invest less. So if you just look at the average investment, it goes down, but not because they're investing less, it's because they live in high capital states more. Okay, so outages go down by about 18%, okay, under full commitment. Okay, they don't go to zero. You don't want zero outages, it's too expensive. And this is the robustness to alternative valuations of reliability. So, okay, just one quick thing before I get into the other papers. This became more acute recently. Like the way you should think about it is the U.S. electricity infrastructure. A lot of it was built in the 50s and 60s. Okay, where people were moving to suburbs and everything was new, and the lifetime for that stuff is like 50, 60 years. Okay, so in the last few years, it's sort of been getting worse and worse. Okay, especially in states that have like a lot of snowstorms and wind. Okay, so around the Chicago area, the reliability had been pretty dismal for a while. Okay, and what they did in Illinois is they actually bypassed the Public Utility Commission. They said this regulation stuff's not working. We're just going to pass a law that gives them money to invest in distribution and improve reliability. Okay, so that's what they did. So on that Energy Infrastructure Modernization Act, okay, that's going outside the regulatory process. Here's what the firm who got the money, they were happy about this, said about it. Okay, so $2.6 billion, okay, bringing greater stability to the regulatory process to incent investment in grid modernization. Okay, and the goals were to improve reliability on the order of 20%, which is okay, roughly what we're getting in the commitment counterfactual. Bunch of weak.
Think about a commitment counterfactual, just saying we're going to do this and we're going to keep it forever, or it's just not credible.
This is different. This is another way to do it. Just give them money to invest. Yeah.
True. But it might not be as efficient as doing a commitment.
Yeah. So it's kind of the commitment. I think of more like a benchmark. Yeah, because it's not clear how to implement it exactly. Because governments change, the parties change, and so on.
It's not true that if I write a contract on the future, I can uphold it in court.
There's a big legal debate on that. I mean, it's true to some extent, of course, but like the further it gets in, and then when it's the government, can it tie the hands of the future government? like the current government can't say the tax rates in 10 years are going to be this. You can't write that contract, right? Because the next government needs to be able to come in and do their.
But
Yeah.
this is a private contract. I mean, the case, the tax rates, that's a public.
Yeah, it's different.
Action.
Yeah, there are limitations on commitment, and it's yeah.
But what is the incentive of of ComEd to use this money for good purposes?
Oh, I mean that. Yeah, they're monitored by the law, and the law's got a lot of provisions to. It's not just a blank check. You know, there's some way of implementing that. I'm sure there's leakage. You know, I'm sure some funny bits. Illinois, I'm sure stuff is happening. But yeah, we do see. So one thing we did is this was passed around 2012. We see investment post. Investment did go up in distribution capital, much more so. If you look at the surrounding utilities, like in Michigan, Wisconsin, Missouri, so the Illinois utilities had an increase in investment. Okay, there's a bunch of weaknesses. For the sake of time, let me. Okay, so what I want to do, I wanted to spend a lot more time on these two papers. I apologize that we didn't get to them. These are two really nice papers. They're about environmental regulation. What they're about, I encourage you to read them. So let me just give you whet your appetite a little bit. What's in there? Okay, so it starts with Stephen Ryan's job market paper. He was on the market, I think, 2006. Came out in Econometrica in 2012. They're looking at cement plants. So cement goes into concrete. It's like a powder. Okay. To make that powder, you got to heat up these kilns to like 1,500 degrees Celsius. Okay. So it takes a lot of energy. It produces a bunch of pollution. Okay. So after electricity and transportation, it's one of the big polluters. Okay. And then this legislative amendment to the Clean Air Act came out that restricted how much pollution you can have. Okay. Put on change the cost of the cement plants. Okay, and he's looking at how investment, in this case building new plants, changed before and after the regulation. Okay, so he has a dynamic model of entering the cement industry. Okay, and tries to back out the cost of entering from the behavior before and after the policy change. Okay, then so that's a change that actually happened. So that's like a retrospective analysis. Then with some co-authors, Fally and Rigwan, okay, they take that model and they add some stuff to it. They add imports, okay, mostly. And they add CO2 emissions. Okay? And with those, they ask, what would be the effect of cap and trade regulations in this industry? Okay? And the main sort of economics is, so one thing, typically economists on the right push is they say we shouldn't do any environmental regulations because China's not going to do them. And if we do them, all the production is just going to shift to China or Mexico, and we're just going to end up importing it. Pollution's going to be the same, and we just lose money. Okay, so they're trying to get at those economics. Okay, trying to devise schemes, evaluate those claims. Okay. In the original Ryan paper, he's only measuring the cost, so the benefits are cleaner air. There's a whole literature in environmental economics. He's only measuring one side of the equation. There's a big. Let me get to the model quickly. Okay, so he's got a demand function, a per period cost function. Then firms are deciding whether to enter or not the industry, whether to build a new plant. Okay, there's a cost of building a new plant that's unobserved. Okay, part of that cost is all the environmental stuff you have to do. Okay, really what he sees in the data is that after the regulation, entry went down. Okay, so he's going to interpret that as costs went up. Okay, and that's the effect of cost on that's the effect of the environmental regulation on costs. Okay, so that's how you can quantify the cost of the regulation. You want to trade that off against the clean air benefits. Okay, then getting to the, sorry, I know I'm skipping. Getting to the follow-up paper, okay, they take that model, and one thing they notice in the data is that imports are going up. Okay, so this is domestic production, domestic consumption. For a long time, they weren't importing any. Okay, then around the 80s, imports start to go up, and you can see it. The gap between these two is imports. Okay, so imports were becoming more and more important. So you want to entertain the notion that cap and trade might lead to leakage. Okay, leakage that is production outside that just gets imported. It's not a crazy argument. Okay, so they add that import margin. They add emissions, has an output kind of like in a BETO where you have the sulfur emissions and quantity of multiple outputs. And they simulate pollution reduction policies with different schemes for awarding the permits in cap and trade. There's sort of the textbook auction off the permits. Okay, there's sort of a political economy motivated award permits by grandfathering old plants. Okay, there's a sort of scheme where you allocate permits in the future based on how much firms are producing. And there's this, I think this is the nicest part, is this border adjustment tax, where you basically tax the imports based on where they're coming from, okay, and how much pollution those countries have. Okay, and that's what solves the leakage problem. Okay, is that border adjustment tax. Okay, so each one of these lines corresponds to different schemes. Okay, and then kind of like how there is uncertainty about the cost of public funds, there's uncertainty about how bad CO2 pollution is. So they use a range. Okay, and so if we look at, these are capacity cement prices. If we look at emissions leakage, this is the thing that people worry about. Okay, and then also total emissions, you can see that the border adjustment tax, okay, leads to low emissions leakage. Okay, yeah, so I apologize. We went a little bit fast on the Ryan papers. You guys, and the follow-up, you guys should have a look. I wanted to talk about more stuff. So we had this taxonomy of regulation. Okay, so we did the antitrust. There actually are dynamic papers about merger control. Okay, really nice one, a theory paper by Volker, Nokia, and Mike Winston, the JP, sort of a dynamic version of Farrell and Shapiro. Okay, they're thinking about when should I approve mergers, realizing that other firms might want to respond with more mergers in the future. And they have a computational paper where they look at the issue of commitment in a dynamic merger game, okay, with investment and capital. And then on the environmental side, there's a nice paper a working paper by Kang and Silvera, thinking about when do you want to give the people who actually implement the environmental policy, who actually go and measure the pollution at different plants, when you want to give them discretion, when you want to centralize that authority, or when you want to let them use their information. There's some interesting trade-offs there. Okay, so there's a lot of other stuff that I didn't get to that I just want to point out some other papers I don't like. Okay, so to wrap up our regulation module, okay, we started with under this taxonomy, the sort of basic canonical theory ideas. Okay, we looked at empirical papers, merger simulation, ex post evaluation, product variety, okay, collusion. I think John did a really nice job talking there, and both the intersection between collusion and mergers in the coordinated effects papers. Okay, then in economic regulation, both static and dynamic papers, and then some of the papers in environmental regulation, both static and dynamic. Okay, I'm done. Yep.
Thank you.